if you remember implicit differentiation in Calc 1, assuming that was in Calc 1, we had a relation between x and y that may not necessarily be a function. And we might be interested in finding out information about its derivative. And so instead of solving for y, we can just look at this relation between x and y and assume that there is somewhere there is going to be y is implicitly a function of x, instead of y as an explicit function of x. Because if we were to try to force this to be an explicit function of x, we have to break it up into two functions, and that's just for this example, and you have other examples where it could be broken up to many more. And so what we can assume is that somewhere along the line we can think of y as a function of x for portions of this graph, and maybe not the whole thing. So it might be good to look in the dictionary and look the definition of explicit and implicit, see what they actually mean, and then it kind of applies. You know how sometimes math terms are different from regular terms? But I think this explicit and implicit in this scenario is pretty close to what they actually mean in math. So implicit differentiation for a problem like this, we think of y is an implicit function of x. So instead of solving for y as an explicit function of x, what we do is we treat it implicitly, and like I said, somewhere along the line we can trust that it is going to be a function of y, which means, you know, there's no vertical line test business. It works out okay. So do you remember implicit differentiation back then? All right, so implicit differentiation, we're going to ddx it, is what I usually say, this whole equation, and we take the derivative of x squared with respect to x. What do we get? 2x. We get 2x. And we take the derivative of 2y with respect to x, assuming y is a function of x. So what do we do there?
2y.
So this is where if y is actually an implicit function of x, and we're taking the derivative of this with respect to x, then we are kind of forced to use the chain rule, because we're assuming that y is the inside function of x. Yeah. Yes. So we ddx the whole thing, so we have to do the right hand side as well, and the derivative of 1 is what? 0. And then you would solve for dy dx. So that's the idea back in Calculus 1 of implicit differentiation. But now we can think about implicit differentiation in Calc 3 as well, because we've studied the quartic functions, and those are relations between x, y, and z that are not necessarily z by itself as an explicit function of x and y. So this is in Calculus 1. This is the kind of stuff that we did. So now let's extend these ideas to functions of two variables, where the third variable z is possibly an implicit function of x and y. So in 3 dimensions, let's take I don't know, like an ellipsoid or something. X squared over 3 squared plus y squared over 5 squared plus z squared over, let's just make it over 1, is equal to 1. So we should also be able to find the derivative of z with respect to one of these two variables, assuming, or if we think about, if z is an implicit function of x and y, so we can kind of derive a formula for this, or we could just look at the formula that they have. I think that for this one, I just want to look at the formula that they have. So if we're interested in finding the partial of z with respect to one of the other variables, then we just take, first of all, what we want to do is we want to treat this thing, we can think about bringing the 1 over to the other side, but as long as it's equal to a constant, I think it's going to be all good. But let's just get used to setting it equal to 0. I think that might just be best. So if we set this thing equal to 0, or bring the 1 over to the other side, get x squared over 3 squared plus y squared. I suppose I could just call it 9 and 25, huh? Plus z squared, and then minus 1 is equal to 0. Just so it's set equal to 0, that would just be a good standard for us to try to keep. And then we can call this a function f that has 3 variables, x and y and z. So it has those 2 independent variables, x and y, and has a dependent variable z, where z is an implicit function of x and y. So all that's left for us to do is to figure out which partial we want. Let's just say we want the partial with respect to x, partial of z with respect to x. And this tells us that we're going to take the derivative of this function, which is really this whole thing. So the derivative of f with respect to x in the numerator, and then we'll take the derivative of f with respect to z in the denominator. And then if we put that as a ratio, then we should be good. So derivative of this thing with respect to x, this looks like it's going to be just 2/9 x. And then everything else is constant with respect to x. And then the derivative of this with respect to z is just 2z. Everything else is constant with respect to z. So that's really all your answer is. I guess you can simplify this. But that's it. What? Say it again? Oh, yeah, it does matter. They're both negatives, huh? Okay. So I don't know if there's much more to talk about this other than you guys get to try this a couple times with your homework. So, yeah.
So this is telling us basically like the slope of a ellipsoid on the sides.
All right. So this is the slope of the ellipsoid going along the x-axis. All right. So let's see if we can get the visual here. This is an ellipsoid, right? And the relation here is you have a function of x, y, and z all together. And what you could do is you can explicitly solve for z. But when you do that, you're going to have two different parts. And so this is where it becomes cumbersome. This is why we want to keep the implicit relation between x, y, and z versus splitting this up. So now, if we're interested in finding the slope at some point, and for that we have to give the actual point. Let's say, I don't know, some point. And then you find the derivative in the x direction. The slope of this line going in the x direction, that's what this is, or this will help you find it. Okay? And the freedom here with implicit differentiation is that you could be given the point, some x naught, y naught, and z naught point, and then you just put it in here. And you don't have to think about whether you have to use this function or this function, because you could just use this for its derivative. Because when you choose a point, you're assuming that the z that they give you will fall into the correct explicit function. If that made any sense. Okay? Right? This is in where we would hold y fixed, and you would move along the x. And that's a change of z values, so the dz, dx. All right? Okay. I think we're done with this. You guys can work this out. And again, just a simple formula to use, and then type in your answers, and then dig deeper if you want to try to figure out the meaning of this. Because what would be cool is that those functions that they would give you are probably going to be a little bit more complicated than ellipses and circles. So, you know, those implicit surfaces would be something that you might want to try putting in the graph, the 3D plotter, the online 3D plotter, just to see how weird some of those surfaces can look like. Remember this drawing?
Yes.
Cool or what? So, what did we do here? If somebody came up to you, one of your classmates came up to you with a printout of this and put it right in front of you and says, "Can you explain this to me?"
It's like you took a slide and you just slipped it into the function, and then you looked at the slope.
Took a slide and
Yeah,
slipped
like
into
you
the
took
function.
a glass sheet or something, and you just slipped it in while keeping. You know what I'm saying? Yeah, it's like a slice. It's like a little, like, you know, and then you peel off the other part, and then you just look at what it's doing along the glass.
Do you guys understand what she's talking about? So that's pretty much the vision that I was trying to get out of this. So that was good, AJ. This is one of the slides here that she's talking about. It's actually, you got this surface and you cut it with this cutting plane, and then this is the image that you would get. And here we found, vectors and slopes and stuff like that. And the slope there is the f sub y, the derivative of f with respect to y. And then we cut it along the x-axis, and we found the slope going along the x as well. So essentially what we found are slopes of two tangent lines, right? A tangent line going along the x and a tangent line going along the y. So, how many tangent lines do we have? How many tangent lines do we have total? We have an infinite number of tangent lines, right? So, what if I want to find a tangent line with a cutting plane that's not either just flat along the x or flat along the y? Do you see the problem? No. Well, we got the tangent plane already, so that problem's done. So let's see if I could come up with another picture here. Surface? We found vectors. From the last one, we found vectors going along the x and the y, and they're tangent to the surface, so they must be on the tangent plane. And so if you have two vectors that are on the tangent plane, on the plane that you're looking for, you cross them. And then, and then you have a point. So, so instead of making our usual cuts along the x or along the y, like we normally have had, what if we wanted to make a cut this time along a different axis or along a different direction? See that picture? This is my plane. Want to be precise with the picture? Let's see if we can be precise with the picture. This is the plane that we're using to cut the surface. This is our resulting curve after we cut the surface. So we're going to attempt to look at this. There's two ways to look at this. We can look at it from this way or from this way. Yeah?
Why would we want to attempt something like this?
Because we might be interested in finding the slope of the line going in a direction different from the x or the y direction. Or let me rephrase that. We might be interested in finding the rate of change in a specific direction. Wait, let me rephrase that. I want to find the derivative of the function going in a specific direction. Those are all the same thing. It's recorded, so you guys can listen to what I said, because I don't remember. Anyways, there's several ways to get to this. Like I said, there's looks like we can look at it from one way or the other. Let's just randomly look at it from this way. And so we're seeing this vision over here of the surface, or a piece of that surface, the curve that we got after cutting that surface. And I would be interested in finding the slope of this line right here. So what is the slope of that line?
Difference in the angle
It's difference in the angle?
from the x direction to the x tangent.
Well, the x tangent would be... Oh, that's the y. That's the y. Yeah.
If you label this, you label this thing C and this is XY.
Well, that's another issue, right? We have another issue. This is z, clearly. This now is this line right here, which is not quite xy. So we have to kind of be creative with the way we label this. Yeah?
Can we just make the plane a plane and then see where it actually intersects the surface and then take the derivative?
Well, that's what we have.
Right.
So let's make this plane a...
Function, a implicit, I don't know what you want from it.
Let's make this into a line,
And then just put it up in the z.
and then just put it up in a z direction. So let's make this into a line. Can we find the equation of this line?
MX would be.
Those are lines back when we were in third grade. A point and a direction. So we have a point. Let's call the direction D, because I'm not quite sure what direction we're going. So let's call this D. So in the D direction, so our equation of that line in 2 dimensions at least, line in 2D is going to be L of t is equal to x naught y naught plus t times the direction vector d, whatever that is. Okay? That was good. So now, let's call D, actually, we need to break this up into components. Let's call it D1, D2. So this can be rewritten as x naught plus t times D1, y naught plus t times D2. Okay? So now, we're going to take this curve, per AJ's suggestion. We're going to take this curve, and then we project it up onto the surface. So that means I can find the equation of this curve over here in 3 dimensions. Let's call this R of t. And that should equal to, at least the x and y components should be the same, right? So let's call it x naught plus td1 y naught plus t d2. So the x and y component's the same. What, how, where?
So your z is a function of x and y, so just plug in
Plug in the L of t
yeah.
into here. So it'll be f of L of t. So that's our three-dimensional curve. Which happens to be this curve, but we're looking at it kind of flat along the plane. So if we have that curve, we can certainly find the derivative of that, right? And at least we'll get this vector over here, right? The vector, the tangent vector here, which is the same as this tangent vector, except I'm looking at it flat. So let's find a derivative. R prime of t. What's the derivative of this with respect to t, the first one? d1. What's the derivative of the second one with respect to t? d2. Okay, now let's take a deep breath. What's the derivative of the last one with respect to t? It is some chain rule crap, right? So what is that chain rule crap going to be? We need the partial of f with respect to x times the derivative of each one of these things, right? So it's the partial, I'm going to use the other notation, fx times x prime. What's x prime? Times d1 plus fy times the derivative of y with respect to t, which is d2. Chain rule. Looks like a dot product of two things, doesn't it? It looks like the dot product of fx comma fy dotted with d1, d2. So it looks like that's our tangent vector. It's not quite the slope yet, though. It's our tangent vector, but not quite the slope yet. Moody asked, what are we going to call this axis? It's a z-axis going up and down, and is this x, y, x? What axis is that? What axis do we use? Let's use a d-axis. Ask Pat.
Is that the fifth dimension?
No, we're not.
No, it's the direction we picked for the direction.
It's the direction that we picked for the direction of the plane, and so it just seems like it's a good label for it. Instead of in the x direction or the y direction, it's the d direction. Okay. Now, I like to think of the slope as rise over run. And so it looks like the rise would be this term over here. And the run, what would the run be?
Square root d1 squared plus d2 squared? I don't know. Is that right?
Yes. So if we call this the d-axis, that little length over here could be the length of d, square root of d1 squared plus d2 squared. And then we can have our little business of rise over run. So if this is a square root of d1 squared plus d2 squared, and then our rise then would become this thing, fx d1 plus fy d2. Now, so the slope is rise over run, right? So we just this is fx d1 plus fy d2 divided by the magnitude, or the d1 squared plus d2 squared. And being that the top part looks like a dot product, we'll peel that out. And then we have this denominator that looks kind of peculiar. What's the denominator equal to? So that essentially makes it seem like it should be a unit vector. Where u is really the direction divided by its magnitude. We're going to come up with this expression quite a bit, where we make a vector out of the partial derivatives. So we probably should define that as something special. But before we do that, this is a special formula called the directional derivative. So what this is really is a derivative in any direction we want now, not just x and y, but in any direction we want, we can find a derivative. Okay? So that's kind of cool. We just now derived it. So if we go in the x direction, what should we get? So let's recap. The derivative of z is equal to f of xy in the direction of u. U is a unit vector. Is given by. Now there's a notation for this. Capital D stands for the derivative of f in the u direction. The derivative of f in the u direction is given by a partial of f with respect to x partial of y, or f with respect to y, dotted with u. All right? So back to my question. What's the directional derivative of f in the x direction? Your unit vector is your I, right? It's 1, 0. So what should your answer be is what I'm asking. It should be fx, right? So this is fx, fy, dotted with I, which is 1, 0. And that's just fx. And that makes sense, because if I'm going to, this direction in the I direction, it's like that cutting plane over here along the x. And the slope here is fx. So similarly, the directional derivative in the y direction is going to be fx, fy, dotted with 0, 1, and this is going to be fy. Okay? But now we can find the directional derivative in any direction. All right, before we do an example, let's come back to this vector over here that seems to hold some important information about derivatives. So we'll call this I guess this is a definition too, although we derived it, so I don't know if it would be called a definition. But this one definitely is a definition. This is the gradient. So the gradient of a function of two variables is going to be a two-dimensional vector. First of all, the notation. More notation. We're going to call it a vector. It's an upside-down triangle. And then we're going to identify the function that it's a gradient of f. And this is going to equal to that vector whose partial derivative. First component is a partial with respect to the first variable, and the second component is a partial with respect to the second variable. Sometimes this is also known as grad, as in gradient, grad f. Okay? So in this section that we're dealing with, 14.6 maybe? I don't know. There's two important concepts. There's the directional derivative and there's the gradient. So the directional derivative is defined. Next time we'll do a bunch of examples of finding out directional derivatives or derivatives in some direction. And this, by the way, can be extended to more than just functions of two variables. We can go 3 or more variables as well. So we'll do some examples of that. And now the gradient is introduced in this section as well. And the gradient is a seemingly simple vector, but it has a lot of important properties that's related with tangent planes and tangent vectors and tangent lines and stuff like that. And so we will see all those properties next time as well for the gradient. Okay? So the main focus now is directional derivatives and gradients. Okay? All right. I think we're done with the lecture portion of today's class. If you're interested in taking the test, or the last 2 pages of the test, I mean, you can hang out. If not, then see you later.